Hello everyone. So this week's tutorial is based on homework number 6. So homework number 6 solution is actually provided on your Moodle shell, and it can be found under week 7 under week 7 section, right? So let's get started with this week's tutorial. There's a total number of 4 problems that needs to be solved, and it's quite a lengthy tutorial actually. So let's get started with this week's tutorial. So problem number 1: a satellite is orbiting the Earth at an orbit height of 4,000 kilometers if a transmitter station is located at one extreme of the diameter of coverage with a coverage angle of 35 degrees and an elevation angle of 5 degrees, and a receiver station is located at the opposite extreme of the diameter of coverage, elevation angle of 5 degrees. Find A, the total straight line distance from the satellite to each station, to each of the Earth station, assuming the radius of Earth is approximately 6,370 kilometers, right? So for this particular question, we'll be using the sine and the cosine theorem, right? So the sine and the cosine theorem is given over here. So now going back to this particular question, the information given on this particular question can be plotted, right? If we draw a rough sketch of this, right? Let's say there's a station 1 that is on this Earth, that is my transmitting station S1. The other station is S2, that is my receiving station, right? And then this S represents my satellite. So whatever information I need to send to one of this station, from if we need from one station to another, we have to use the satellite as a medium, right? So both these satellites are having an angle of elevation of 5 degrees. So in that particular case, okay, yeah. So in that particular case, what happens is if let's just consider one side of this, right? So if you have this curvature representing the Earth's surface, right, and this particular line over here representing the radius of the Earth, right? So this also cuts through this line over here. So what happens is that you can draw a triangle with this with the center of the Earth, right? Considering this center of the Earth and the Earth station and the satellite, we can draw a triangle over here, right? So in this particular triangle, what happens is this part is the radius of the Earth, right? So basically, this will be the radius of the Earth. This side over here will represent the height of the satellite from the Earth's surface, plus from here, this point from the Earth's surface till this center of the Earth is my radius, right? So this particular side will be represented by h plus r, right? And then if we need to find the total, this particular distance, that from the distance between the satellite and the Earth station, right, will be represented by d, right? So if we have a triangle of such, right, the same triangle could be made for station 2 as well, right? Isn't it? Right? So considering the center of the Earth with station 2 and the satellite, we can draw a triangle for that as well. Now, since both the triangles, both the substations are having an angle of elevation of 5 degrees. So in that particular case, what happens is the angle of elevation is actually measured from the horizon, isn't it? So what happens is the horizon, since Earth is a round surface, isn't it? So the horizon will be basically the tangent to that particular Earth surface, right? So the angle of elevation is 5 degrees. So that will be these 5 degrees will be measured from the horizon, right? So horizon is basically the tangent line running through the Earth's surface, right? At that particular point. Same goes over here as well. So the angle over here is 5 degrees, right? The angle over here is 5 degrees. The angle of elevation is 5 degrees. And this particular tangent is 90 degrees to the Earth's radius, isn't it? So that is 90. Same goes for here. If this is 90 and this angle of elevation is 5 degrees, what happens is both the sides, this is the radius, this the Earth's radius as well. So we have two angles. This angle and this angle being of same size, right? So what happens is we can see that this triangle, this side is identical to this particular side. So if we find the distance for one satellite to the Earth station, right? If we find 1D, that is the same distance for the other side as well, right? So that is why, since both the satellites are having the angle, the elevation angle of 5 degrees, right? Both the satellites are having the angle of elevation of 5 degrees. So basically, we'll be just considering one triangle, right? So basically, take one triangle, and that will be the same distance of the satellite to the other the other Earth station as well, right? So the other side as well. So now we know that the angle, this angle from this side to this side, the total angle from here till here is 90. I mean, sorry, 5 degrees plus 90. So there is going to be 95 degrees, right? So the angle over here is 95 degrees, right? And the angle of coverage between this satellite and the Earth station is given by 35 degrees. So basically this angle over here is 35 degrees. So let's say beta is equal to 35 degrees. So if beta is equal to 35 degrees, this particular angle is 95 degrees, right? So basically we can see that we can write we know our h, right? In this particular case, our h is 4,000 kilometers. And our r value is this, right? So our r is equivalent to 6370. So what happens is this total distance could be found, that is h plus r, that is equivalent to 10,370 kilometers, right? And we know this particular, we need to find this particular side. So we have this particular side, but we know, this particular side is unknown. However, the angle opposite to this particular side over here is known, that is 35 degrees, right? This angle over here is 35 degrees, right? And we know this particular side, right? That is h plus r value. And we know the angle opposite to this side as well. So in this particular case, we can use our sine rule. So using the sine rule, if we write the, write the equation for using the sine rule for this, these two sides and these two angles, that will be basically d upon sine of the opposite angle, that is d upon sine beta, right? Or sine 35 degrees, right? I'm not sure if you can see this. So that will be d upon the opposite angle, that is d upon sine of 35 degrees, that is equal to this particular side, that is h plus r upon the sine of the opposite angle. So the angle opposite to this side is 5 degrees plus 90, so 95 degrees. So h plus r upon sine 95 degrees, right? This is 95 degrees. And from this, we know the h plus r value, that is h plus r value is 4,000 plus 6,370. And we only have one unknown, so that is d. So we can solve for d. So d is equal to h plus r times sine 35 degrees upon sine 95 degrees. Knowing h and r values, that is 4,000 and 6,370 respectively. So we can solve for d. So d value is basically equal to 5,970.7 kilometers, right? So this is the value for d. And this is the same distance of the satellite to one Earth station, and that is the same distance to another substation. The distance between the other Earth station to this satellite, right? Moving on to part B of this particular question, the diameter of coverage. So the diameter of coverage of one satellite to the pardon me. So basically, let's say let's just avoid what I just said. So let's say the diameter of coverage. So we need to find this particular part over here. Let's say the Earth station, the satellite is located somewhere here, right? And the line that runs from this particular the satellite is this, right? and this is the line for the in this same particular diagram, let's just go to this particular diagram. If you can see this particular diagram, there's the satellite, right, and the two Earth stations. So basically, we need to find the angle, the diameter of coverage that is from this point to this point. So basically, we need this particular coverage over here, and the Earth is round, isn't it? So we just need to find this particular distance, this particular perimeter, S, right? So that is what is represented over here. So basically, we need to find this particular area that is being covered by the satellite and the one of the Earth station. So this particular S, right? So we know this beta value. So in that particular case, this particular angle is known, that is 35 degrees. And knowing that this Earth is circle, we can use the perimeter, the formula for finding the perimeter of a sector, that is basically given by S is equal to 2 times beta times R. So this particular value from here till here is particular value. This S is basically given by 2 times beta times R. This is the perimeter of a sector, where beta is given in radians, right? So we know our beta value, that is 35 degrees. So we have to just convert that beta value into radians. So that converting 35 degrees into radians, we'll be getting 0.61, right? And we know the radius of this particular circle, right? That is the R value. That is the radius of the Earth. That is given over here. That is 6,370 kilometers. So directly substituting the beta value in radians and the radius of the Earth, can find our S. So that is basically equal to S is equal to 2 times 0.61. That is the radians in the beta value in radians times 6,370 kilometers. So the diameter of coverage is equivalent to 7,782.42 kilometers. Moving on to part C of this particular question. The delay in the round trip transmission of one signal from one base station to another. So the round trip basically means the signal traveling from one station through the satellite to other, and then back to that particular same to the starting station, right? So in this particular case, that will be the total round trip transmission delay. That is basically we know this particular. I mean, like the first thing is, let's say the distance. We know the distance between S1, right? If we draw the I mean, if we take this representation of satellite, the satellite and the Earth substation, right? We can draw a figure something like this, right? If we draw a free body diagram of that, right? In this particular case, there will be a time delay from S1 to satellite, right? So let's say we are using this as a transmitting station. So there will be a time delay from S1 to satellite that is known as T1. So we know this particular distance, right? This T that we have calculated in part A of this particular question, that is 5,970.7 kilometers. So we know the distance, and since it is traveling in free space, so the speed will be the speed of light. So basically we can calculate the time. So the time based on the formula for speed, that is speed is equal to distance divided by time, making time the subject of the formula. Time is equal to distance divided by speed. In this particular case, speed, since the signal is traveling in free space, we'll be using speed of light. So time needed, time one or T1 for the signal to travel from S1 to the satellite is given by T1 is equal to D upon C. Then there will be a delay from satellite to S2, right? Satellite to S2. Again, this T is same as this T. Remember, over here, since the angle of elevation is same for both sides, so the distance from one distance between the satellite and one station is equal to the distance between the satellite and the other station, right? So D over here is equal to the D over here as well. So again, whatever time is needed to travel from here to here is also the time needed to travel from here to here as well. So in that particular case, again, T2 is given by D divided by C. Right? So the distance here is same as this one, right? So D upon C. Then, since it's a round trip, then there is a reply that needs to go back, right? So the message is here. Now that same message has to go back to S1. So it will go from here to here. Again, T3 is equal to D upon C. And then there's a delay from here to here as well. So that is also given by T4 is equal to D upon C. Since the distance over here to here and the distance over here to here is same, and the speed of traveling is also same, so the time taken from here to here is same as the time taken from here to here, and the time taken from here to here is same as the time taken over here to here, and time taken from here to here is also same. So in that particular case, the total time, the round trip for the total time is given by T is equal to T1 plus T2 plus T3 plus T4, which is equal to 4 times T, right? So since T1, T2, T3, T4 are all equal because of the distance and speed of light being same. So T1, T2, T3, T4 will be all same. So basically we just need to find one time and then multiply it by 4 because T1, T2, T3, T4 are equal. So we know our distance, that is 5,970.7 kilometer, right? So that in meters, because our speed of light is in meters as well. So that would be 5,970.7 times 10 to the power of 3 meters upon 3 times 10 to the power of 8 meters per second. So that will give me a time of 19.9 milliseconds. Then what I need to do is to multiply this time by 4 in order to get my total time delay. So that is 19.9 times 4. The total time delay is basically equal to 79.6 milliseconds, right? So that covers question number 1. Moving on to question number 2, or problem number 2. A satellite orbiting the Earth has a round trip time delay of 45 milliseconds when communicating with a single Earth station located within its area of coverage. Remember, for this there was 2 satellites. In this particular case, there is a single satellite. Remember, there is a single Earth station, right? This single satellite located within its area of coverage. If the Earth station elevation angle is 10 degrees and the straight line distance between the satellite and the Earth station is h, find the satellite orbit height. So again, drawing the similar triangle to this particular question over here, using the center of the Earth, the station, I mean the Earth station and the satellite point, right? We can draw a triangle. So we need to find the satellite height, that is h over here in this particular case. We know the Earth's radius, that is 6,370 kilometers, given in the first question. So we know this particular r, we know this particular r value over here. So we need to find our h, and this d is unknown as well. So we can find this d based on the time delay over here, right? So it says the round trip delay. So since we have one station, so the message will be sent from this substation, from this Earth station to the satellite, and then from the satellite back to this same particular Earth station, isn't it? So the total time for that is 45 milliseconds, right? So the time for one path will be basically, it is the same distance being traveled in both paths, right? From S1 to S and back from S1 to the time taken from S1 to S is same as the time from S to S1 as well, right? So the time will be equal since the distance is equal. So in that particular case, the time taken from the signal to travel from S1 to S is basically half of this particular time, right? So that will be basically equal to 22.5 milliseconds, right? So that is the time taken for the signal to travel from S1 to S, all right? So we know the time taken from S1 to S. So that is 22.5 milliseconds, and the signal is traveling in free space. So we'll be using speed of light. Again, using the formula, speed of light is basically, speed is basically equal to distance divided by time. We can find the distance t, isn't it? Because we know the speed, that is speed of light, and we know the time, that is 22.5 milliseconds. So finding out d, that is basically equal to 3 times 10 to the power of 8 milliseconds. Again, that is the speed of light times this time, that is 22.5 milliseconds. So our distance is basically equal to 6,750 kilometers, right? So we know this particular D, we know this particular R value, that is 6,370. We know that the angle of elevation is 90, so the angle of elevation is basically measured over here, that is 10 degrees, and that the horizon to the Earth's radius forms 90 degrees. So 90 plus 10 degrees, the total angle from here to here is 90 plus 10, that is 100 degrees, right? So we know this particular angle, that is 100 degrees, right? And we need to find our h. We know this distance, d, and we know this side as well, that is my r. So using the cosine rule, right, we can write the cosine rule for this particular side. For this particular side, that is basically given by h plus r squared is equal to this particular side, that is r squared, plus this particular side, square of this particular side, that is d squared, minus this 2 times this two side, that is 2 times r times d, times cos of the angle opposite to this particular side. Since we are writing the equation for this particular side, so times cos of this particular angle opposite to this particular side, so times cos 100 degrees, right? So I believe all of you can write this, because this was this is basically from your high school maths, right? So this is the equation, right? Using the cosine rule for this particular side. Based on this particular equation, we know our r value, that is 6,370 kilometers. We know our d value, that is what we have calculated, that is 6,750 kilometers. We what else do we need? Yeah, so we can solve for h plus r, right? Isn't it? So if we solve for h plus r, basically you can take whatever value you get after substituting this value, right, and the r value on this particular side and taking the root of that, you get h plus r equal to 10,053.47 kilometers, right? And then from this particular equation, we know our r, then we can solve for our h. So solving for our h, we get 3,683.47 kilometers, right? So there's an error in this particular there was some error in this solution set, so I've corrected it and I'll be passing this solution back to you, right? So that is why I've crossed off this solution and I've written the solutions using through this particular print over here, right? So moving on to part B of this particular question, that is find the coverage angle. Again, to find the coverage angle, now, right, now we need to find the coverage angle. So coverage angle is between the angle covering S1 and S, right? Or the H station and the S, this particular angle over here, that is beta. So using the sine rule, now that we know this h plus r side, right? We know height, that is h, and we know the radius over here. Using that we have solved, the height is this, right? And the r value is this. So we know this particular side, right? And the angle opposite to this, we also know that, right? That is 100 degrees. We need to find this angle. However, we know the side opposite to this, so we can write the sine rule. So writing the sine rule, that will be d upon sine beta. Beta is what we are looking forward to, right? And d is what we have found over here, right? That is 6,750 kilometers. So d upon sine beta is equal to h plus r, right? H plus r upon sine 100, upon sine 100. Solving for sine beta, so sine beta is basically equal to d upon sine 100 upon h plus r. Substituting, making beta the subject of the formula and substituting all the values, we'll be getting beta is equal to 41.39 degrees, right? So that is simple evaluation over there. Moving on to part C of this particular question, diameter of coverage. Again, diameter of coverage is this part over here, right? This angle over here. So you can see this is the perimeter of a sector, and that is given by 2 times angle times radius, right? So the angle should be in radians. So S is equal to 2 times beta times R. So in this particular case, beta is given by, beta should be in radians. So beta value is 41.39 degrees. So converting that into radians will be 0.72 rads, right? So that is 0.72 rads, and the radius of the Earth is 6,370. So substituting the values, you'll be getting the S is equal to 91.72 9,172.8 kilometers, right? Part D of this particular question, it says if a second Earth station is used inside the coverage area with an elevation angle of 5 degrees, what is the distance of this Earth station to the satellite? Right? So what is the distance of this Earth station to the satellite? So the angle of elevation is 5 degrees. So again, we can draw a triangle using the center of the Earth, the Earth station, right, on the surface of the Earth, and the satellite, right? So that will form a triangle. So we need to find the distance of the Earth station to the satellite. So basically we need to find this particular distance over here, right? And this is my S2 vector, right? So from here to here, so we need to find this particular distance over here. So we know the radius of the Earth. So that is my radius of the Earth, that is 6,370, right? And the angle of elevation is 5 degrees. So if the angle of elevation is 5 degrees, that is 5 degrees plus this tangent forms 90 degrees to the radius. So that is 5 plus 90. So that is going to give the angle over here from here to here is 95 degrees, right? Okay. So the angle over here is 95 degrees here to here. We also know the height of the satellite from the Earth's surface. I mean, the height of the, we know the height of the satellite from the Earth's surface that we have calculated over here, right? So this particular side is basically h plus h, right? Plus the radius of the Earth. So that is h plus r. So h plus r value is that what we have found over here. That is 10,053.47 kilometers, right? Okay, this is the unit for this is in kilometers, right? So we know this side, we know this side is unknown, and we have one angle that we know, that is 95 degrees. So we can use the cosine rule, right? So if we write the since we know this particular angle, so we have to write the cosine rule in terms of this particular side. So that is going to be h plus r, right? So h plus r squared plus d squared plus r squared, right? Minus 2rd, right? Cos this particular angle that we are using, that is 95 degrees, right? So using the cosine rule, if we write the equation for this particular side, this is what we have. So now that we have this particular equation, we need to find this d, isn't it? So what we can do is, you can see that we have d squared over here and we have d over here. So it is somewhat equivalent to a quadratic equation, isn't it? So taking this term to the other side and rearranging the terms, we will be getting d, rearranging this term. So that is d squared, right? D squared. And then next is this particular term that has d. So 2r cos, 2 times r cos 95 degrees dot d, right? Rewriting this plus this r squared plus r squared. And since we are taking this to the other side, that will become negative of h plus r squared. And there is nothing left on this side, so that is equal to 0. So just observing this particular equation, you can see that this is a quadratic equation, right? So we can use a quadratic formula. So quadratic formula is given by x is equal to minus b plus minus root of b squared plus 4ac. Sorry, b squared minus 4ac divided by 2a. So in this particular case, our x is the d value, right? X is equivalent to d, and a, b, c is the coefficients. So a is the coefficient for d squared. So a is the coefficient of d squared. That is a is equal to 1. The coefficient of d is equivalent to b. So b is basically equal to minus 2r cos 95 degrees. So the R value is given by 6,370, right? Throughout the following equations. I mean, from the previous questions, right? That is given over here. The radius of the earth is 6,370 using that, right? Using that, we can evaluate the coefficient B, that is going to be 1110.36, and the coefficient of C, basically the coefficient of D to the power of 0 or nothing, right? So that is going to be this particular part over here, right? That is going to be my coefficient C. So that is basically r squared minus h plus r squared, right? In this particular case, our r plus h value is 10,053.47, and our r value is 6,370. So using these two values, you'll get C is equal to minus 604,95359.04, right? Once we have the A, B, C values, we can basically solve for D, right? Remember, X is equivalent to D, right? So we solve for D, since there will be two values because of this plus and minus, right? So we will get two values for D. So two values of D, that is 7,242.49 kilometers and negative 8,352.85 kilometers. So since the distance cannot be in negative value, we'll be considering the positive value, right? So this will be the distance, or this will be the value for D over here. So the distance between the second Earth station and the satellite is basically equal to 7,242.49 kilometers. E, the delay time of a single way transmission from one Earth station to other Earth station using the satellite as a relay station. So basically, you need to send a message from station 1 to station 2. So we know this D1, right? Remember D1, the distance D1 was basically calculated in part A of this question, right? The distance of satellite 1 to, the distance between Earth station 1 and the satellite, that is 6,750. So D1 is 6,750. And the distance between the satellite and the Earth station 2, that is what we calculated in part D over here, that is equal to 7,242.49 kilometers. To find time, right, knowing that the message will be traveling at the speed of light, so you can find time. Time is basically given by distance divided by speed, that is equal to, so the time from here to here is given by 6,750 times 10 to the power of 3 divided by 3 times 10 to the power of 8, that is going to be 22.5 milliseconds. And then the message will travel from the satellite to the station 2, that is going to be T2. So T2 is basically given by D2 upon C. So in this particular case, my distance 2 is 7,242.49 times 10 to the power of 3 divided by C, that is 3 times 10 to the power of 8. You will be getting 24.14 milliseconds. So since it's a single one-way transmission, so it will be just message traveling from S1 to S2. So you just need to total T1 plus T2. So you'll be getting 46.64 milliseconds, right? So moving on to question number 3. So question number 3 is based on advanced mobile phone systems. So the mobile phone systems or the cell towers basically are shaped, cover a area in a hexagonal base, right? Basically, it is in a honeycomb structure. So this could be, I think I've passed on the textbook to you guys, so you can read more about the wireless communication or mobile phone structures, right? So based on this particular problem, an AMPS or Advanced Mobile Phone Protocol System, right? Advanced Mobile Phone System. A mobile system is assigned a bandwidth of 1.8 megahertz using 20 kilohertz channels with a cell radius of 6 kilometers. Find the total number of frequencies allocated to the system, that is part A. So the total number of frequencies allocated to the system, since AMPS is based on FDM, so one frequency is equal to one channel, right? So basically we need to find the number of channels. So number of channels is equal to total number of bandwidth divided by channel bandwidth. So in that particular case, 1.8 megahertz divided by 20 kilohertz, that is going to give me the total number of channels or frequencies as equal to 90. Okay, so we need to know the number of channels required to cover the same bandwidth. So they will be needing total of 90 channels to cover the total bandwidth of 1.8 megahertz. Part B, how many cells are needed to cover an area of 10,000 square kilometer? So in this particular case, we need to cover this particular area. So how many cells are needed? So like I said, a cell covers a hexagonal area, right? And usually it is, all these cells in a particular area forms a honeycomb type of structure, right? You can, let me just open your text. So you can see a area being covered by, let's say an area covered by a set amount of towers. So it will be basically in a honeycomb type of structure, right? And each structure is going to be covering a hexagonal area. And since yep, so yeah, so you can read more on this in your textbook, basically on cellular wireless structure, that is starting from page 268, right? So you can read more about mobile phone communications over here, right? And the formulas that we are going to be using over here. So coming back to this particular question over here, how many cells are needed to cover an area of 10,000 square kilometers? So basically we need to find the area of a hexagon. So the area of this one cell is a hexagonal area. So area of one cell is basically given by 1.5 root 3 times r squared. So in this particular case, our r is given over here, that is 6 kilometers over here, right? So r is 6 kilometers. So substituting our r into this particular formula, we'll be getting 93.53 square kilometers. So we need to find the number of cells. So number of cells is basically equal to total number of area divided by cell area. So that is equal to 10,000 divided by 93.53. That is going to give us 106.92 cells. Remember, cell towers cannot be in fractions, so that is why we have to round it up. So in this particular case, that will be 107 cells. So 107 cells is required to cover this total number of area, right, over here. Next is next is if frequency reuse is used, what is the pattern needed to obtain a maximum of 13 frequencies per cell? Remember, a cell is what do you say is there's a bandwidth that needs to be covered within an area, right? A set amount of area. So each particular cell or each particular frequency will be covering, or each particular subchannel will be covering a particular amount of bandwidth, right? So over here, that is what we found. That is a total number of 90 channels were required in this such case, right? Now that we are saying that frequency reuse is being done. So each particular cell now uses 16 frequencies. Each particular cell now can at a time can utilize or handle hitting different frequencies. Over here, each particular cell was basically dealing with one particular set of frequencies. If we are using frequency reuse, so how many cells will be required in that particular case, right? So a total of 90 channels were required to cover the same amount of bandwidth. Now that we are using frequency reuse, where 13 frequencies being handled by each cell. So in that particular case, number of channels on the frequency reuse factor will become, or can be calculated as total number of channels. So that is 90 channels, right? Divide by the channel special is basically given by total number of channels divided by the frequency reuse factor. So the frequency reuse factor is basically given by total number of channels divided by number of channels special. So in that particular case, 90 channels are there, and each particular cell can handle 13 cells, right? In this particular case, or 13 frequencies. So that is basically 90 divided by 13. So the frequency reuse factor will be basically 6.92. So we'll need a total of 7 cells in a frequency reuse network to cover the same amount of bandwidth, right? So let's say, yeah, this same, let's say there will be 7 cells covering this amount of bandwidth. So this forms a cluster. So we need 7 cells forming a cluster to cover the same amount of bandwidth, right? Or 1.8 megahertz, whereby each particular frequency cell represents or covers 13 frequencies or 13 channels during a frequency reuse, right? So frequency reuse factor is equal to 7, or basically number of cells in a cluster, right? So using that pattern, how many channels are available to the system? So using that pattern, how many channels are available to the system? So the number of channels in total is basically given by 13 channels per cell, and how many cells are there within this particular area? In this particular area, there is 107 cells, right? So in that particular area, there is 107 cells, and each particular cell covers 13 channels. So 13 channels times 107 cells, that is equal to 1,391 channels, right? Okay. Part E, what is the minimum distance of the core channels, right? So minimum distance of a core channel. Just before I touch on this, right? Just covering on this. Let me open your textbook, right? So this is what it implies, right? Initially, there's a certain area that needs to be covered, right? There's an area that needs to be covered, and in that area, we have how many cells? Based on our question over here, we are using 107 cells, right? And in a particular mobile system, in AMPS mobile system, we need to cover this many bandwidths. So this many bandwidths is we need to cover this many bandwidth, and using 20 kilohertz channels. So basically, we need to cover this much of bandwidth using 20 kilohertz channels, right? So basically, we need 90 channels to cover this particular bandwidth. And when we are using frequency use, so basically what happens is 13 frequencies is being represented by each cell, or 13 channels is represented by each cell. So a total of 7 cells, or 7 the frequency reuse factor is 7. In that particular case, 7 cells cover this particular bandwidth, right? So what happens is, this is what happens, right? So let's say we need to cover 1.8 megahertz. So we need 7 cells, right? These 7 cells over here that forms one cluster is covering 1.8 gigahertz of, 1.8 megahertz of frequency, and each of these cells cover each of this particular cell cover 13 frequencies, where 13 frequencies or 13 channels, whereby each channel size is equivalent to 20 kilohertz, right? So that is what it says, and then this same cluster is then spread out into this large area, right? Okay, you can read more about this in this particular textbook over here, right? The textbook that I have given out, right? Excuse me. So since we are running out of time, so I won't be able to explain each and everything, but for this particular question over here, So in that particular area, how many cell towers that needs to be there? That is basically equal to 13,000, 13. I mean, sorry, how many, sorry, this particular question said how many channels are needed to cover this particular area. So basically you need 107 cells. So 107 cells is covering this particular area. So how many channels are needed to cover this particular area? That is 13 channels per cells times 107 cells. That is going to be equal to 1,391 channels needed to cover this particular area, right? Part E of this question says, what is the minimum distance between the core channels? So again, going to this particular textbook, the core channels are the distance between this one in this particular cell tower, right? One to its neighboring clusters cell one tower, right? So the distance between here to here, right? What is the distance between here to here? That is what is being asked, right? So going back over here, so the distance between one cell, right? Distance between, okay, let me open this text. The distance between this to here, from 1 till this 3, let's say from this cell to here, this cell is given by, based on your textbook, that is given by, that is basically given by root 3 times r, right? So r is the radius of the particular cell, right? So root 3 times r is the distance between one cell and another cell. Now, if we need to find the distance between one channel and its co-channel, or this particular channel in this particular cluster, to the distance of the corresponding channel in the other cluster or neighboring cluster, distance between one in this particular cluster and one in this particular cluster is basically given by this particular formula, right? D times root of n. N is the cluster size or the frequency reuse factor. So basically B, right, this formula is actually wrong, right? So let's omit this. So basically D is equal to root 3 times R. So root 3 times R value is 6, right? 6 kilometers. So root 3 times R, that is 6, times root of n. So root, our n value was, or the frequency reuse factor was 7. So root of 7, right? So root of 7 times root of 3 times 6 is going to give me 27.5. And remember, this radius is in terms of kilometers. So it is the distance between the core channels will be also in meters, in kilometers, right? So the minimum distance between the core channels is basically equal to 27.5 kilometers, right? Problem number 4. Let's move on to the last problem. That is problem number 4. The bandwidth available to a single operator in the AMPS system is 30 megahertz with a channel bandwidth of 30 kilohertz. If the following parameters are applied, right? This is the cell area, the area covered, the average number of calls per user, the average holding time of a call that is given over here, call blocking probability that is given over here, and the frequency reuse factor that is being given here. Calculate the number of channels per cell, right? So calculate the number of cells per channel. So number of channels per cell is basically given by number of channels upon the frequency reuse factor, right? Or the n value. So in this particular case, we can find the number of channels. So number of channels is basically equal to, we know the bandwidth size, right? So the bandwidth is 30, the total bandwidth is 30 megahertz. So 30 megahertz, and each, and we are using a 30 kilohertz channel. So the channels, the number of channels is basically given by total bandwidth divided by channel bandwidth. This is equal to 30 megahertz divided by 30 kilohertz. So basically we need 1000 channels, right? 1000 channels to cover this same bandwidth. So we need 1000 channels. So the channel per cell is equal to number of channels divided by frequency reuse factor. So in this particular case, frequency reuse factor is given over here, that is 12. Number of channels is what we have calculated, 1000. So number of channels per cell is equal to 1000 divided by 12, which is equal to 83.3. Remember, the number of the values are usually in integer order, integer values, right? number of channel special and the cell values, all these are all integer values. So that is why we have to approximate it to the nearest whole number. And that is going to be equal to 83 channel space. So moving on to the last part or the last question of this particular tutorial, this week's tutorial, that is B, the total traffic carried per cell. Use the elang P table shown below with the linear interpolation. So basically, elang is the unit of measuring the capacity, right? Using or measuring the total traffic carried per cell, right? It is the unit, and this is the table that we need to use, right? So number of servers, or the n value, the number of servers, is basically equivalent to the number of channels per cell. So that is what we have calculated over here, number of channels per cell over here. So we have to find its capacity. So you can see that these values are given into a set amount of values, right? So it says use the elang B table, right, shown below, and use the interpolation. So interpolation means you have to linearize this particular part over here in between these values and find the middle part, right? Interplot the values and find the value for which you are looking for this for which you are looking the solution for. So you can see that 83 is not visible over here in this particular table. So our 83 value falls somewhere over here, right? Right. So 83 is not present. So 83 column is not present. So we'll be using these particular values to interplot, right? 70 and 100 is what we need to plot. And the probability, so the probability that we'll be using is the call blocking probability is 1%, right? That is given over here. So the call blocking probability is 1%. So that is represented by 0.01. So basically we'll be using this particular column over here, right? So we need to interpolate this 70, the number of servers over here, or the number of channels per cell, 70, and its capacity, right? And 100 cells per channel, 100 channels, 100 channels per cell with its capacity, and try to find our capacity at 83, right? So we have to interpolate these values, this and this, with this and this, right, in order to determine the value for, or the capacity for 83. So what we do is we can plot if we draw a graph, right? If we draw a graph, the number of channels per cell, or number of servers, number of channels per cell against the channel capacity, that is A, right? Let's say that is represented by A. So let's say this particular column is representing A value, and this particular part is representing the number of cells per channel, number of channels per cell, right? So if we plot this particular values against this particular axis over here, so at 70 channels per cell, we have a capacity of 56.1, right? At 70 channels per cell, we have a capacity of 56.1. At 100 channels per cell, right? At 100 channels per cell, we have a capacity of 84.1. So we have to interplot these 2 points, right? Or plot this, right? Interplot this so that we can find the value for 83. So what we need to do is find the equation of this particular line, right? These 2 points, right? Find the equation of the line for these 2 points, so such that we can find the value at 83. So the gradient of this particular line, right? This particular line can be given by y1, right? So y1, so this particular axis is my y-axis, this particular axis is my x-axis. So basically y1 minus y2, y2 minus y1 upon x2 minus x1 is the gradient formula, isn't it? So using that particular formula, that is a2 minus a1 in this particular case, because y is represented by a and x-axis is represented by this cc, right? Let's just represent it as cc rather than saying as channel per cell, right? So in this particular case, m is basically equal to a2 minus a1 divided by cc2 minus cc1, right? That is the gradient, the the formula for the gradient of a line, right, for 2 points, that is equal to the A2 value is 84.1 minus 56.1 divided by 100 minus 70. That is going to give me a gradient of 0.93. So this is my gradient. Now, what I can do, what I know is I can write the equation of this line, right? Isn't it? However, the equation of the line is given by y is equal to mx plus c, right? Let's just avoid this, right? In a moment, right? So yeah. Oh, okay. Sorry. The formula was already given over here. So you can see that in this particular case, our y-axis is represented by a, and our x-axis is represented by cc over here. So in an ordinary mathematical equation, m is given by y2 minus y1 upon x2 minus x1. Since our y is represented by a and our x value is represented by cc, so directly rewriting it, so we'll be rewriting the equation in terms of this, and solving for m, we'll be getting 0.93. Now the equation of a line is basically given by y is equal to mx plus b, right? So in this particular case, rather than using x and y values, we'll be using a in place of y and x in place of so we'll be using a in place of y and cc in place of x, right? So in this particular equation, and we have to find the b value, right? We have found the m value. Using this, we have to find the b value. So b is basically equal to y1 minus mx, right? So you can use any y and x value, right? You can either use these two values or you can use these two values. So what they have used is these two values, right? 184.1. So directly substituting the values, right? Remember, this is represented over here, right? So in this particular case, y value is 84.1, and the x value they have used is 100. So 84.1 minus the m value is 0.93 times the x value. So x value over here is 100. That gives me the b value as minus 8.9, right? So sorry about this. The equations were written over here, right? So once we find the b value, we can rewrite this whole equation, right? So we know our m, we know our b. We need to find, so we can write the equation, right, for this particular line. So that will be basically equal to, remember, y is represented by a and x is represented by c. So in this particular case, a is equal to, right, we can rewrite this as a is equal to m value. A is equal to m value, that is 0.9. A is equal to 0.93. X is basically cc, so x is cc plus b, so b value is minus 8.9. So this is the equation for this particular line. So now we need to find the value at, or the capacity at 83. So directly substituting 83 value in place of cc to find the capacity or the a value. So in that particular case, our a value is equal to 68.29 LR, right? That is basically the capacity for the total traffic, the total traffic carried per cell, right? Or the capacity for each cell is basically equal to 68.29 LR, right? So this is the solution for the last question over here. So with this, we'll end this week's tutorial. So it was a lengthy tutorial, so excuse me about that, right? So yeah. So with that, we'll end this week's tutorial. Like I said, this is just a recorded video. I had already run the tutorial session, so I had already taken the solution. But however, I promised you guys to prepare a better video for everyone, since only 2 students attended. So this was just for a video recording, right? Purpose. So if you have any other queries, you can always email me or drop me an email, or you can directly Viber message me, right? Okay. I believe all of you have the textbook. So yeah. So with that, we'll end this week's tutorial. Thank you.